I believe we are ready to start, unless you have other ideas. So this is our second lecture in the course on quantum transport and topology, right? I will learn it eventually, the name. So I will start with a short recap of what was the last time, the main points that we discussed in the previous lecture, and we discussed classical diffusion, which is described by the diffusion equation. Diffusion equation contains a diffusion constant and we in a much detail discussed what the propagator of this diffusion equation is. Propagator, which is also called the diffuson, is the object that in momentum and frequency representation looks like this: 1 over dq squared minus I omega. And we also discussed the Einstein relation, which is the relation between the diffusion constant and the electric conductivity in a metal. So if conductivity in a metal happens because electrons can diffuse, and this is how the conductivity is related to the diffusion constant. And also we had an expression for this diffusion constant, which is Fermi velocity squared times tau divided by the dimension. So that's more or less all we had last time. And what we are going to do today is we will again rederive all these things, but now using quantum mechanics. So last time there was nothing quantum, it was just usual classical diffusion. And as we all know, classical mechanics is the limiting case of quantum mechanics. So in principle, it should be possible to use quantum mechanics to derive all the same results. And this is also needed because later we will use the same quantum mechanics to derive something that goes beyond these results. Some quantum effects that are not classical. So if there are no questions to the last lecture, we begin today something which is called quantum transport, if you like. Transport means any effect when you have a current, when something flows somewhere. Okay, so the main object that we are studying is a metal with impurities, and electrons in this metal scatter on the impurities. So we will describe everything in terms of the following object, which is called the green function. Green function for electrons. Green function of electron. Let me put it this way. And actually, a little confession. When I was a student myself, I had a very rough time understanding what the green function is. It took me like a few years.
In many body or single body?
That was exactly the problem.
In single body, it's sort of easy to understand. In many body, to me, it's just a name. I don't get why it's called that.
That's a good point. The problem is that in any textbook, or almost in any textbook, there is a very general definition that applies immediately to many-body problems. And we will not consider, at least for now, any many-body problems, so we define the green function as an operator. Green function is actually not a function, it's an operator, and this is the definition. It's some number E, which is energy, minus the operator H, which is the Hamiltonian, inverse. That's the definition. It's just the inverse operator to this. And Hamiltonian is something that is a basic object in quantum mechanics, so hopefully it, so if you like, I can even put a hat on it. It's an operator. And it just turns out that this operator, which is G, is not really well defined when this is energy, and this is just a parameter, it's a number. But if this energy coincides with some eigenvalue of the Hamiltonian, it might happen that this thing in brackets has an eigenvalue 0, E minus H may have a 0 eigenvalue, and it cannot be inverted. So to avoid this thing, we add here some, or subtract some very small imaginary number, and then we call it, if we add plus I0, it's called the retarded green function, and if we subtract, it's called the advanced green function. And we put the index R or A. This here is retarded, retarded, and this sign here means advanced. So once again, it is still an operator. We just, and the Hamiltonian is a Hermitian operator, so all eigenvalues are real numbers. Energy is also a real number. This difference is real, and this thing is imaginary, so this whole thing can never be 0. Whatever you do with the Hamiltonian, if you do this shift in the imaginary direction, you avoid any possible singularity. Later we will, but for now, for the definition, it's enough to define it like this. Okay, so once again, this is just the operator, which is the inverse of another operator, and this other operator is the Hamiltonian, and for the Hamiltonian, we also assume something. Hamiltonian for electrons in a metal contains two parts, H0 plus V. So this H0 corresponds to clean, pure metal. This is clean metal, and V is the disorder or impurities in this metal. And I am writing it as is usually written for perturbation theory. So these impurities provide some small perturbation to otherwise clean metal. Okay, and once again, the Hamiltonian of a clean metal is an operator. They are all operators, but this Hamiltonian usually is just a function of momentum. What does it mean, the operator is a function? It means that in momentum representation, it is a diagonal operator. So if you know the momentum of electron, you know the energy. It's just what is usually called the dispersion relation. Yeah, it's like p squared over 2m. It's a function. And for the impurities, usually this V, this perturbation, is a function of R. It's a diagonal operator in real space representation. So we have some potential. It's like an external potential. Each impurity has some local potential, whatever, bump or dip that scatters electrons. So one part is diagonal in momentum representation. The second part is diagonal in the real space representation. So the sum of them, we don't know. It's not easy to diagonalize in a general way. That's why we will do a perturbation theory. We will assume that this impurities contribution is a small perturbation, and we will do an expansion in powers of this V. Yeah. So, yeah, before we do this expansion, one last thing. There is, you see, there is always this difference, energy minus Hamiltonian. And actually, nobody knows where the zero of energy is. You can count energy from any level. And you can easily add any constant to this energy and add the same constant to the Hamiltonian. They will cancel out, so this constant has never any physical significance. So it is usually easier to count energy relative to the Fermi level. Fermi level will be zero energy. So we will say that energy is the Fermi energy plus epsilon, plus some deviation from it. And for the Hamiltonian, we will do the same. We will say that Hamiltonian is Fermi energy plus a deviation, and this deviation has a standard name. It's called psi of p. It's still a function of p. We just subtracted a constant. And Hamiltonian counted from the Fermi energy is usually denoted psi of p. In a simple case, when our metal is, when we have this parabolic spectrum, as we discussed last time, so this is momentum here and energy here. This is the Fermi level. And energy is p squared over 2m, or whatever. And if we subtract from this, so this is the Hamiltonian, p squared over 2m is the Hamiltonian. If we subtract Fermi energy, psi of p is, in that case, is p squared minus p Fermi squared divided by 2m. And here, p is the operator, and p Fermi is a number. But they are vectors, actually. P is a vector. It has a direction. P Fermi actually also has a direction, but in this particular case, it's the same in all directions. The length of this vector is the same. And we will study only small deviations. Epsilon will be small correction to the Fermi energy, and psi will be a small deviation from the Fermi level. So in our case, P will be almost equal to Fermi momentum. And we can say that this thing approximately is, you see, it's the difference of squares. It's P minus P Fermi, P plus P Fermi. So it's like P Fermi divided by M times P minus P Fermi. Or we can say that this is a V Fermi, the Fermi velocity, times momentum minus Fermi momentum. And this actually here, momentum is a vector, so it's an absolute value of P here. And this is also a very standard form. Psi of P is this thing. It does not contain any knowledge about mass of electrons or anything. It's just the Fermi momentum, which is the radius of the Fermi surface, and Fermi velocity, which is the slope of spectrum near this point. So, yeah, so this is how to represent psi in a well-defined way. We don't need this quadratic thing here. We can just write it this way.
Quadratic thing if you want to write it as number. You can't really take an absolute value of the derivative.
Well, actually, I can, but it's not advisable.
Okay. Okay.
Sorry. So far, no physical
No, there is a physical reason, which I also mentioned last time. We work in the semi-classical limit, which means that Fermi energy is much larger than inverse tau, inverse mean free time. So by subtracting this large Fermi energy and concentrating on the vicinity of this window is the...
I guess when we see it how just directly from the Hamiltonian that you wrote, tau should somehow be encoded in V part, right?
Yeah, tau is the characteristic of the disorder.
I mean, you will expect so the energies of interest are roughly on the order of the frequency
Inverse tau.
of the field which is being applied. So as long as that frequency is small in comparison to EF, you're probably fine.
Yeah, so if we do all this, we can rewrite the green function in a very similar way. It's epsilon minus psi of p minus v of r plus or minus I0 inverse. Now this expression does not contain any Fermi energy or any notion, any non-universal parts. So epsilon counted from Fermi level, psi is this thing, it contains only universal parameters, v is whatever. So this is the proper way to define the green function in a metal. And now we do what I mentioned already, the perturbation theory. We assume this v here is a small correction to the rest. And we can take this object and do an expansion in powers of v. So first of all, I will define the same green function, g, the same as this one, but without impurities at all. It's called the clean green function, or g0, epsilon minus psi plus minus I0 inverse, just this, without v. And if we do an expansion of this object in the series, the first term will be just g0, something without this v. And then next term will be linear in v, and this next term is g0 times v times g0. Then next term is quadratic in v, and it is g0 times v times g0 times v times g0, and so on. Believe it or not, this is how the inverse function is expanded in a series. It's almost a standard geometric series. The only thing you should care about is the order here, because they are operators, they do not commute. But if you put them in this alternating order, this will be the correct way to expand this thing here. And actually, it's very easy to prove. This is very easy to prove because I can, let's do it this way. I can take G0. Actually, I will not prove it. It's obvious. It's the sum of geometric series. So this is a geometric series, and the sum of it is like G0 inverse minus V and inverse once again, which is exactly this thing. So why do we use green functions, and why do we represent perturbation theory in terms of green function? Because there is a graphical representation of this thing, which is called a Feynman diagram. So for G0, for this clean green function, we will picture it as a straight line. You can put an arrow, or you can not, or you can omit this arrow. It doesn't matter. So this series is represented as G0. This is the first term, plus the next term contains two green functions, two straight lines, and V, which is in between, is shown as a cross, just like this. And then this term is a line with two crosses, and so on. So once again, G0 is a straight line, V is just a cross. In some sense, if we do everything in real space representation, V is a function of R, it's diagonal in real space, so in real space it's a single point. And G is not diagonal in real space, so it has some extent, goes from one point to a different point. This is actually an electron propagator, so how electron propagates from one point to another. V is just a function of R, and it exists only at a given point, and doesn't propagate anywhere. So this series and this thing here, I can also put arrows if you like, it's just the same thing, and they both represent the green function of a disordered metal. Green function of electrons in the presence of impurities. And if you like, you can also think of these crosses. Each cross is like an impurity. So it's literally, to go from point A to point B, electron can either do it ballistically, just fly according to its Hamiltonian from one point to another, or it can fly but being scattered once somewhere on some impurity, or being scattered twice, or being scattered 3 times, or being scattered any number of times. And if you add up all this, this will be a total amplitude from going from one point to another point. So I should add some more assumptions about this V of R in order to proceed further. So I have written this expansion, but we can do nothing with it if we do not assume something about V of R. And what we will assume is the following thing. It's a very standard model which is used almost always. It's called Gaussian white noise. White noise disorder. So you have a metal, you have impurities there, and they are random. It's some random variable. This V of R is some random function of R. And what we assume about this function, we don't say what it is. We don't give a particular function. We just assume what the distribution is. It's a random function, which at each point is random, and it has a Gaussian distribution. Gaussian distribution means that at every point, V of R is on average 0. We just select it this way. We have a Gaussian function. V can be positive or negative. On average, it is 0. And if we take V at 2 different points, R and R prime, and average the product, it will be also 0. Except when R equals R prime, which means it is a delta function of R minus R prime. So white noise, sorry, no, it's...
Do we add a number?
Yes, in a minute. So when I say white noise, this is exactly what I mean. It's uncorrelated in different points. And in a single point, when R equals R prime, there should be some number which quantifies how strong this disorder is. And this number is 2 pi nu tau. Actually, nu is the same nu as here, is the density of states. And tau is the same tau as here in the diffusion constant. So the stronger are your impurities, the larger this V's, the smaller is the tau. So tau, the mean free time gets smaller, gets shorter when you have stronger disorder. And I will prove just today, later, that this is the correct number to put in this formula. You can put just any constant. Then you do all the computations, you can derive the diffusion constant, you can derive conductivity, you can derive everything. And in order to get this value for the diffusion constant, for example, and this value for conductivity, you have to say that this constant is that one. They are just related. Yeah. as I said, I do not assume any particular function v. I assume it's a random function. So I have, if you like, I have many realizations. I have not a single sample. I have million samples. And in each sample of the same material, I have some different distribution of impurities. And then I can average over these samples and say that on average, the potential at a given point is that one, and on average, the correlation. Averaging over ensemble, it's called. Once again, I will do all the calculations, not for a given function v of r, but for the whole distribution, and I will always compute average quantities over this distribution. Sorry? Was it not enough mathematical averaging over distribution? No?
You can, I think you should define it. Like you can define it with backwards if you want. You can define it as a functional integral over a Gaussian distribution function, but that's a bit.
Yeah.
That's a bit silly to do.
Yeah. Okay. So the first thing to calculate is this is our green function, right? This series here is the green function. So the first thing to compute would be the average green function. Let's take our green function and compute its average over the distribution. Yes?
So do I understand correctly that these two averages is enough to say that all the higher averages we're using?
Yeah, actually I assume Gaussian distribution. So Gaussian function is fully defined by its mean and what's the name for this? Yeah, and the variance. So if you like, this is the mean, this is the variance, and the whole function is Gaussian. Yeah, so let's average. What will happen with the first term? It's G0, yeah, it does not contain any V, so it's on average equal just itself. What will happen with the second term? It contains V here, average V is 0, so yeah, on average, this thing does not exist. What will happen with this term?
You have a correlation between two.
Yeah, we have two V's here. Yeah, like in this expression, V and V. This one is, I can write it, let me write it explicitly. This product, what is written here is G0 from point R1 to point R2, V of R2, G0, R2, R3, V of R3, G0, R3 to R4. I just put these numbers, of course, randomly. So I have written the product of operators, of matrices, in real space representation. In real space, V is diagonal, depends only on one R. G in real space representation depends on 2 points. It's a matrix. It's like matrix indices. And then I do contraction, how I usually multiply matrices. This is a diagonal matrix. These are not diagonal matrices. And I have to sum over all indices here, which means I have to integrate over R2 and 3. And then it will depend on R1 and R4, on the initial point and final point. So if I want to average this thing, I take these two V's here at point R2 and R3. I remove them and replace with this average. So I will have a delta function R2 minus R3 divided by 2 pi nu tau. So in fact, it's not a double integral, it's just a single integral because of the delta function. Points R2 and R3 will coincide. I will not compute this integral, of course, because I didn't even tell you what the green function in this real space representation is. I will just say that this whole thing can be drawn as a picture with these two crosses, and I connect them with a dashed line. And So this dashed line is the correlator of two v's. So the average v average is a dashed line, and it's a delta function. It's once again, it's already written there with this amplitude. So in this diagram, what I have is three green functions, 1, 2, 3, and one dashed line. 3, 1, 2, 3 green functions and one dashed line. It's just the illustration of this integral. So when you average green function, what happens? You take these two crosses and you just connect them with the dashed line. Let me do the following. I erase this term because it's 0. I will put this average g here. Average g equals clean green function, and this is the next term. And I will continue this series. What if I have 3 crosses? If I have 3 crosses, on average it's again 0 because it's an odd number, and any odd power on the Gaussian distribution averages to 0. And then the next term will have 4 such crosses, 4 of them. So what happens if I try to average the product of 4 these, 4 such functions? I gave you only the average of 1 and 2. And yeah, for the Gaussian distribution, it's a known property which is sometimes called Wick's theorem, that the average of the product is you can do a pairwise averaging in all possible ways. So actually it means that I can connect with the dashed line these 2 crosses. This is one option, plus I can connect the same 4 crosses this way, plus I can connect the same 4 crosses this way. And that's all. All the next terms will contain more than 4. Once again, in each picture here, each dashed line is just a delta function. It's just this object. It's very simple. I mean, in real space, it's just a single point. And in momentum representation, it's just a number. It does not depend on momentum, because Fourier transform of a delta function is a constant, is unity. Okay, so average green function equals this, plus this, plus this, plus this, plus this, and so on. Still no idea what the whole sum is. So what should we do? We do what people usually do in the diagrammatic calculations. They define something which is called an in this case it's called a self-energy. Self-energy. I will first draw some pictures, and then it will be clear what this whole thing means. Self-energy is the following thing. Sigma equals this object plus this object plus this object plus some other objects. And the average green function equals usual green function plus usual green function with the self-energy inserted plus the usual green function with self-energy inserted twice, and so on. So actually what happens? We take these diagrams for the green function and we say, this one is a irreducible diagram. This one is the irreducible diagram. This one is the irreducible diagram. This one is reducible. Reducible means that it can be cut in two disjoint parts by cutting just one green function here. So all irreducible diagrams I collect together and call them the self-energy. And then I can insert this self-energy many times, and this diagram, this represents all possible reducible diagrams because I have this green function shown in the middle explicitly. The next one will be reducible in 2 points, reducible in 3 points, reducible in 4 points. It's just pure combinatorics. I can take all the diagrams and I can rearrange them such that I collect all irreducible diagrams in a self-energy, and then I can insert this self-energy once, twice, 3 times, or any number of times, and it will count all possible diagrams in the end. If I substitute this into here, I will just restore the whole series. So once again, self-energy is the same diagram for the green function without the outer parts. These outer functions are not included. These outer functions are not included, such that if you cut any solid line, it will not break into two disjoint parts. For example, if I tried to do this, if I took this thing, it is not a part of self-energy because I can cut it and it breaks into disjoint parts. That's why this is reducible, and this is a part of this term. It has twice the self-energy here. Once this from self-energy, and the second time the same part from the self-energy. Is this clear? Great. So, average green function, we can do this summation. It's again a simple geometric series as we did with V here. So V is replaced with sigma. You see, it's the same series, but V is replaced with sigma. So if we do this summation, we will see that G on average is epsilon minus psi of P minus sigma inverse. That's all. Sigma is some operator. I mean, it's the sum of these things. It can be quite complicated. But as long as you know self-energy, you also know the average green function. And we have reduced the problem of calculating the green function to the problem of calculating the self-energy. And this one is a bit easier. You can just count. Here I have 1, 2, 3, 4, 5 diagrams. And inside the self-energy, I have only 3. And if I insert them here, they will reproduce all these 5 diagrams and many more. So, let me erase more stuff here. How do we compute the self-energy? Actually, it is still an unsolvable problem. There is no any exact way to find the self-energy exactly, but there are some approximations that can do it quite well, and the first one of them is called Born approximation. Born approximation. Yep.
So such a representation of self-energy means that we change the order in which we sum all these terms. But in case if this series doesn't converge, it can be non-trivial that we can change the order of summation.
Well, so first of all, it does converge.
Okay.
Second of all, we are doing physics and not mathematics. That's why we don't care.
So it doesn't necessarily converge.
No, this I mean for Gaussian distribution, it does converge. Yeah, it might happen that it is not very well convergent. You're right. There are some tricks, but in what I will just show you, this it all works just like that.
Because otherwise, the result can depend on the way in which you sum your terms.
Yeah, this is true. This is true.
I once solved
this is also possible. Something will diverge already in the Born approximation. Just watch. Born approximation is the following approximation. We take our self-energy, and we say self-energy equals this diagram, and that's all. All other diagrams are thrown away. In some sense, it means we are trying to say that each dashed line is small thing. If we have only one dashed line, it's one, but if we have two, it's already much smaller. If we have three, it's already much smaller. It's in a sense the same perturbative approximation as we used here. We somehow assume that V is a weak correction. So Born approximation in metals is actually a very good approximation. It works perfectly. And we will right now compute our green function within this approximation. So we should calculate this diagram here. And this diagram contains one dashed line and one green function. So dashed line is 1 divided by 2 pi nu tau with a delta function there. And the green function is 1 divided by epsilon minus psi of p plus or minus I0. And there is an integral over all momenta, ddp divided by 2 pi power d. That's all. So in momentum representation, the dashed line is just the number, 1 over 2 pi nu tau. In momentum representation, the green function is this thing. And when I connect them, I have to integrate over momentum that goes inside this loop, so this is that integral. There is a momentum going inside the loop, and dashed line does not depend on it, it's a number, and the green function does, and it's this dependence. So, how do we compute such an integral? As I already told you, actually the green function is not this, it's an approximate green function. The exact green function is E minus H. E minus H. And this thing works only close to the Fermi energy. We have some approximate psi of p close to the Fermi energy, and we have epsilon, which is close to the Fermi energy. And this thing actually, both are small. Epsilon is small, psi is small, so this denominator is small, which means that the green function is large. And if we go away from the Fermi energy, or away from the Fermi momentum, there is nothing small in the denominator, and then the green function is not that large, and actually this integral captures the main part, the main contribution which comes from the vicinity of the Fermi surface, from the vicinity of the Fermi energy. So we don't actually have to compute the integral over all momentum in the whole momentum space. We can concentrate on momenta close to the Fermi momentum. And this is a very common trick. It is done like this. Whenever you see an integral over all momenta for something that relates to a good metal, you replace this integral, just replace, with nu is a number, times the integral over psi, and times the same object, the same dots, averaged over directions of momentum or velocity, doesn't matter, velocity, Fermi velocity. So what does it mean? Imagine we are living in a two-dimensional space. This whiteboard is our whole world, it's two-dimensional. And then this is the momentum. X component of momentum, Y component of momentum. And then we have a metal, and it has a Fermi surface. It's a circle with a radius PF. PF is the radius, PF. all states inside are filled with momenta inside are filled, all states outside are empty. So instead of integration over the whole px and the whole py, we integrate only in some narrow strip around. We take the integral only in this strip. And to do this, we say that each point has some direction of velocity. This is the Fermi velocity. It's a vector. It has different directions in different points. And d psi is the variable that changes from here to here. So psi equals 0 on the Fermi surface. It's a little bit. It's positive when we go out of the Fermi surface, so our energy grows. It's negative when we go inside. So we can, instead of this two-dimensional integral, we can say it's an integral over the radius, which is represented by psi, and over directions. And actually, nu is the correct factor here. So the density of states has exactly this meaning. How many states we have in a given energy window. D psi is the energy window, nu times d psi is the number of states in this window, and this here also counts the number of states. In any dimensions.
No, it's exactly 2 dimensions. In general dimensions, it's...
You mean for parabolic spectrum?
Oh, yeah. Okay, that's true.
For parabolic spectrum, yes. For not exactly. For parabolic spectrum in 2 dimensions, this is exact if you say that there is a lower limit, which is minus a Fermi here, up to infinity. And what I will do, I will say just minus plus infinity. Hoping that the integral actually converges somewhere near the Fermi surface, so I don't care what the limits are. Yep.
So, I mean, if we would want to do it like from the very beginning, then psi p would be defined by like a crystalline structure, right? Alright? For example, it would be cosine p, and we would just have an integral from over the Brillouin zone. So, like physically, this integral always converges. But we use some approximation, like sitting in quadratic spectrum.
No, we don't use approximation of quadratic spectrum. I understand your question. So just imagine you have a Brillouin zone.
Yeah, I mean, maybe just
Yeah.
one sentence, because formally speaking, like for example, imagine that d equals to 2, or 3, d equals to 3, and then I just even without the quasi-classical approximation, I just substitute in psi of p like p squared, and I have an integral like p squared divided by p squared, which diverges.
If you substitute p squared here,
Yeah.
it means you are unlucky. You are unlucky. It indeed diverges.
So the way I incorporate it is that, formally speaking, there is like cosine or some kind of...
Yes, you're right.
I integrate only over Brillouin zone, right?
You're right. There are different ways to make it convergent if you need. Another way would be to replace this delta function with some function of the finite radius.
But what is like the physical reason?
It's called the correlation length of your random disorder.
Okay.
No, man, it's some advanced topic. I will talk a little bit about it just shortly. And about the Brillouin zone, you can have, as I mentioned last time, you can have any spectrum, not parabolic, any just literally any energy is any function of P. This is energy. And this is your Brillouin zone from here to here. And then it's periodic, if you like. Then you have your Fermi level. And you say, this is the point up to which I fill my electrons. I fill the spectrum. And then you just say that in the vicinity of these points, I will use the variable which is proportional to energy, which I call psi. I do not care what happens here or there. And then this averaging, it's the averaging over the Fermi surface. So you will encounter all the points where you really cross the Fermi level, and then you have this psi integration will go around each point like this, and averaging over directions will count all these points. Okay, that was unnecessary for understanding. So I would like to compute this integral using this trick. Why not? So the only thing to do, so this is sigma now. I jump over this equation. 1 over 2 pi nu tau. And then I have nu integral d psi divided by epsilon minus psi plus or minus I0. No p, psi is now the integration variable. Any ideas for the value of this integral? Yeah. It's called exactly like you said, but it will not help you. Well, actually, it's a logarithm. That is d psi over psi. It's a logarithm. You can just take the integral.
That's true.
The problem with this integral, yeah, by the way, nu cancels out.
Since you used the approximation form.
Sorry?
You can apply different limits since you used the approximation form.
Yeah, this is true. This integral is not well defined because if I really take it from minus to plus infinity, it diverges. Logarithmically, it's a logarithm. Logarithm of infinity is infinite. But above 0 or above epsilon, it has one sign, and below epsilon, it has an opposite sign. So it diverges to plus infinity in one direction, to minus infinity in the other. So if I put here symmetric limits, these divergences will cancel out. This is exactly the equation you mentioned. It has this principal value part, which cancels out. And then there is another part which is due to this I0, and that one is actually convergent. And the answer is, so I have 2 pi tau here, 1 over 2 pi, wait, let me put it this way. This whole expression has two parts. One is formally infinite, in quotes. It's a real part of this integral. It's either infinite or zero. It depends on how you put the limits. All what Lisa mentioned, it's relevant for this real part. But if you take an imaginary part of this object, then the integral for the imaginary part is convergent, and it does not depend on these limits, and it's very easy. It is minus or plus, depending on whether you had plus or minus here, 2 pi tau, and then a residue is just the residue in the pole is 1, and I take only half of this pole because I go only halfway around, and this is 2 pi tau here, yeah, so it's I over 2 tau. So the imaginary part is well defined. Real part is not well defined, and actually the reason is exactly as was mentioned. The real part does not come from the vicinity of the Fermi energy. It is accumulated over all momenta, also far from the Fermi energy. And it's not actually infinite, it's some random number, which depends on the spectrum. In a brilliant zone, in a fine crystal, it will not diverge, actually. So it's just some number. Let me put it, it's not an infinity, it's a number. But it's real. It's a real number, plus or minus this. And now we take this sigma, this self-energy, and we plug it into here. And what we see is this number from sigma, which I don't know how to compute, just adds to epsilon. Why this is not zero? It might be as well zero. I mean, it depends on how exactly you put the limits and how exactly this psi depends far from the Fermi.
So if it isn't zero, you can just shift the energy.
Yeah. But it's a number. I mean, it's a constant which does not depend on anything. So, to finalize this part, the average green function is epsilon minus psi of p, and then I put sigma here, so it's plus or minus I divided by 2 tau, inverse. So this number, I just absorbed it into epsilon. I said epsilon was a number. It was counted from the Fermi energy, but I added a new one, so my Fermi energy shifted, if you like. I didn't know where it was anyway. So if you add any number, it will be some just a new definition of Fermi energy. This is called renormalization. When you say that you have a parameter which you measure, but then your theory tells you that you have to add some random unknown numbers to this parameter. You say, I don't care, whatever I measure already includes these numbers. Well, they're already added. I renormalize it and I forget about the number. Well, so what do we have? We have our model of a metal with impurities. We assume Gaussian white noise disorder for this impurity potential. This Gaussian white noise disorder introduces the parameter tau. It was not present in the clean metal. And then we calculate the average green function averaged over disorder, and we observe that it's the same as was the clean green function, just this I0 is replaced by I over 2 tau. With the same sign. For retarded function, it is still positive. It was plus I0, it becomes plus I over 2 tau. For advanced function, it was negative, it remains negative. So, are there any questions here? Yep.
So you said that it's not Topology theorem, where it's Topology theorem. So what did you mean?
It will not help you to understand what this number is. You can use it, yeah, you can use it, or you can just take the imaginary part and then it's a convergent integral. You don't need. Yeah, it's for 0, right? But yep. That's a good question. It will be answered in 10 minutes.
Okay. One more question about convergence. So what if we substitute p squared over 2m instead of psi, and then take an imaginary part of this integral, and we'll
You will reproduce the same result, provided if Fermi tau is large.
But it's not obvious that this integral will still converge even after we take an imaginary part, because the denominator increased as pq, and the denominator will increase like p4. Yeah. So, okay.
Even in 3 dimensions, it converges.
But in 4 dimensions.
In 4 dimensions, it doesn't.
Okay.
Yeah.
You mentioned like a physical interpretation of the green function, right? It's some particle which starts at point x and then propagates to point
Yeah.
y. And is there any visual physical representation of the momentum space? I mean, like how to think about, for example, just the fact that it seems that we only moved our green function a little bit away from.
I will show also shortly, and actually I probably should have mentioned this. So we discussed last time the propagator of the diffusion equation, which was the solution to the diffusion equation with the delta function on the right-hand side. So the green function actually is the propagator of of the Schrödinger equation. This is a Schrödinger equation, E minus H times something equals 0 times the wave function. If you replace this 0 with a delta function, the solution will be the green function. So it's a propagator of the Schrödinger equation, and That's why I also mentioned that this is like the amplitude from going from one point to the other, the same way it was for the diffusion, for the propagator of diffusion equation.
So here, this Green's function is not analytic, right? Because usually you expect the imaginary part to drop to zero at the Fermi surface, right? Because then you can have a stable ground state.
It is not analytic. Let me answer. In exactly the same way as it should be. As I mentioned in the previous lecture, diffusion propagator is analytic in the upper half plane of frequency, which is called retarded. And the same is true here. Retarded Green function is analytic in the upper half plane of epsilon. And the advanced one is the opposite. It's analytic in the lower half plane.
But like, even if you were to, for example, now derive the time order one, right?
Oh, please no, I will not.
Then it's literally like, then it is discontinuous at the Fermi level.
Yeah, right. It is discontinuous and it will remain discontinuous. It's discontinuous even in the clean
Basically,
metal.
you have unstable particles.
Wait. It's
Wherever you are.
it's discontinuous even without any disorder.
What?
It is discontinuous without any disorder.
Yeah, with this.
Without disorder, it's already discontinuous.
Well, no, because then the imaginary part is zero, so it's fine. It's at the sort of the pole, well, at the pole it's always discontinuous, right? But
Yeah.
the pole sort of goes to zero and then flips the
Okay,
sign.
I believe we can discuss this after the lecture, but I will never use any time-ordered functions here, only retarded and advanced. So this problem will not be
But like then this means
really
that all
relevant.
particles are unstable.
This is the average Green function. So it's averaged over many realizations. Actually, I will answer to this in a minute. Just let me please move on and you will see what I wanted to say. Actually, I don't see this in my notes. Yeah, here it is. So this is our average Green function. It depends on energy and momentum. Now we will do a standard exercise, which is called Fourier transform. Exercise. How does the Green function look like in, just for definiteness, the retarded Green function as a function of momentum and time instead of epsilon? So to convert from energy to time representation, we do the Fourier transform, the epsilon over 2 pi, exponent of minus I epsilon time, times the Green function. And the Green function is just this, epsilon minus psi of p. And for retarded one, it's plus I over 2 tau. This is a very simple integral. We already did more or less the same integral last time. It was dq squared minus I omega. Why is it plus now? Yeah, now it's plus. Because that was omega and this was as epsilon. Yeah, that's correct. So there are two cases. Case number one, t less than 0, negative times. Negative times means we have positive number in the exponent and the integral converges in the upper half plane. So we have to complete the contour in epsilon in the upper half plane, but the only pole of this expression, epsilon equals psi minus I over 2 tau, the only pole lies in the lower half plane, so for negative time, we get 0. And for positive time, we should complete the contour in the lower half plane. And what we get is I exponential, and here instead of epsilon, we just insert this number. minus I psi of p times t minus t over 2 tau. Yeah, this is psi minus I over 2 tau times t in the exponent. Now the question, what will happen if I do the same thing but for a clean green function without this tau here?
Select the opposite is minus.
Sorry?
Opposite is minus.
No. I mean, if I put plus I0 here.
It will not decay.
I will just replace this inverse 2 tau by 0. So I will remove this part, but all the rest will be the same. So actually, what is written here is the average clean green function times e to power minus t over 2 tau. Average green function with disorder is the same as the, sorry, this one is not average, is the same as the clean green function times this decaying factor. And this is actually what you asked.
So
All particles disappear with time. After mean free time, no electrons left.
okay. All particles decay while particle number is infinite.
Right. And this happens because we look at the average green function. If you take any green function in a given disorder potential without averaging, it will not decay. It decays only as the result of averaging, because in different realizations, your electron is scattered. It can go to the right, or it can go to the left, or it can go up or down. You average, and you see that it just disappeared.
But it also sounds like then you cannot use, for example, effective theory. Then you cannot really find any representation where you have stable surface.
Yeah, that's also correct. But this is not a problem. I mean, we will restore the particle conservation later. It's just an artifact because we look at the average green function instead of the true green function. Okay. So now to the other question, which was about how good Born approximation is. Let's see. So Born approximation takes into account this diagram. Yeah, this is sigma as in the Born approximation. And it also takes into account this diagram because it's twice the same sigma. What Born approximation does not take into account are this and these diagrams. Well, I mean, from this first 5, we took into account 1, 2, 3, and we omit these 2. So let's ask ourselves a question. What is the effect of these 2 diagrams? We can estimate what these 2 diagrams actually provide. And to do this, we will need an eraser. So we have already did something in the Born approximation. Now we will see what happens if we try to include diagrams beyond Born approximation. This thing is not well erasing. Beyond Born approximation. Beyond Born. So we have one diagram which looks like this. I draw the diagrams for the self-energy, not these ones, but these 2, this and this. And we have the second one which looks like this. And we also attach them to some green functions, so we have the outer lines. Now, for this diagram, we have some momentum in the green function outside. We have some other momentum P1 in this green function and in this one. And we have some other momentum P2 in the innermost function. And we have to integrate over P1 and P2. Why do I put momentum like this? Because I know that the dashed line is a delta function. In momentum representation, it means it's a number. It does not depend on momentum, which means that it can transfer any momentum along this line. So this line transfers, what it is, P minus P1. P minus P1. Yeah, we have momentum P coming here. P1 goes further, P minus P1 goes to the dashed line. The same for the second line. It has P1 minus P2 inside. And then when it comes back, it adds up and it becomes P1 again. When this comes back, it adds up and becomes P again. So I have the integration over P1 with two green functions, over P2 with a single green function. And this external one I do not integrate. They are just fixed. I will not do this integral. I just label the momenta. Now let's do the same for the second diagram. We have P outside, and now I have three functions like this, and I will say this one is P1, this one is P2. What momentum should I put to the middle function to satisfy all momentum conservations? Actually, it is P1 plus P2 minus P. So, for this diagram, I have an integral over P1 and P2 of three green functions. For this diagram, I also have an integral over P1 and P2 of three green functions, but they are green functions of P1, P2, and of this argument. I can even write it explicitly if you wish. This diagram is 1 over 2 pi nu tau squared, two dashed lines, integral over dp1, dp2, g squared of p1, g of p2. This one. And the other diagram, also 1 over 2 pi nu tau squared, integral dp1, dp2, g of p1, g of p2, and g of this, p1 plus p2 minus p. This one is independent of the external momentum. This one is dependent on it. It does depend on the external momentum. So, as we already discussed, the green function has a very high peak when we get to the Fermi surface, when epsilon is small and psi is small. And for these three green functions here, I can do it very well. I can say P1 is near the Fermi level, so this green function has almost 0 in the denominator. P2 is also close to the Fermi level, so in this green function has almost 0 in the denominator, and three green functions have 0 power 3 in the denominator. This is very nice. But for the other one, I can say that P1 is near the Fermi surface. I have 1 0 in the denominator. P2 is near the Fermi surface. I have the other 0. But this one is not. This is actually a vector. They are vectors. This one is somewhere, depending on the directions of momentum. So this diagram, so this integral actually is much less than this one. Because here I can satisfy all three green functions at once, and here I can satisfy only two of them. Satisfy the condition that they lie near the Fermi surface. That's why there is a very useful inequality. This thing is much smaller than this one, without any integration. Just by counting and by geometry, we see that this diagram is much larger than this diagram. Once again, it's the same inequality. And this is just an illustration of a general principle I will formulate it somehow. Crosses are small. Whenever you have two dashed lines that cross each other, like here, you get something smaller than if you do the same without crossing. Each crossing of dashed lines makes the diagram smaller. So this one is smaller than that one. For other diagrams with more lines, it's the same. Whenever you have an extra cross, the diagram becomes, each crossing multiplies it with some small number.
Sorry, which parameter tell us that this relation? So it's probably Fermi energy, but the comparison
Look,
with what?
this is the average green function. Yeah, it has tau here. So when I say that I want to get close to the Fermi surface, I want to get close to the Fermi surface at the distance inverse tau. Andrei, the answer to your question, what parameter? Parameter is Fermi times tau.
Yeah, but I'm just trying to understand where you get this tau when you compare these two integrals. When both of them are independent on tau.
Listen, please, to my answer. This is your Fermi surface. It's not a single line. It has a width. The width of your Fermi surface is inverse tau because you have this imaginary part in the green function. So green function has a maximum which has the width. It's not a delta function. It has a width 1 over tau. When you overlap three green functions like this, you can be inside this circle for all three. When you overlap functions like this, you have one circle, then you have the second one of the same width, and then you should compare the area of this circle to the area of this intersection, and this is your parameter, which is the length of the Fermi surface times the width, which is E Fermi tau. Is it clear?
I'm sorry again. I understand this argument, but I'm just looking on two integrals where both of them are independent on tau. You don't have a tau in this G0.
No, you don't need that actually for this argument. You just need to say that the large contribution is like.
Okay, if you don't have tau, this is divergent, and that one is less divergent. With tau, you can really compare them. Yeah. So, yeah.
Why can't we actually satisfy the close to? I
You can, but you have.
You can, but only for certain directions of momentum, not for any directions.
Because you have to find
You have more or less, you have three, once again, you have your Fermi surface, you have 3 points, 1, 2, 3, and the linear combination of them should also get onto the Fermi surface.
And the region is still small.
Yeah, as I just erased here. Okay, so this general principle that any crossing of dashed lines give us a small correction means that we can can neglect this diagram altogether, and all other diagrams in the self-energy that include crossings of the dashed line. And the result of doing this has a name. If we do exactly that, we cannot compute the exact average green function, but if we throw away all the diagrams with crossed lines, then we can. And this is called self-consistent Born approximation. It's some upgrade of a usual Born approximation. Sorry, 1 moment. Approximation, or there is an abbreviation, it's called SCBA. Yeah.
Are the green function in the integral free or floating functions?
Sorry,
Are those
These are zero green functions, I mean clean green functions. Or I didn't hear. What are the two alternatives?
Is it G or G naught?
It's G naught. It's like here, I have a series, it's G naught in every line, and then it's also G naught in every line in the self-energy. So, self-consistent Born approximation means that I take my self-energy, like in the Born approximation, I include this diagram, plus I include all diagrams where the dashed lines do not cross, like this one, or like this one, and so on. All diagrams where the dashed lines do not cross in the self-energy have one common feature. All these diagrams have one dashed line that goes all the way around from the initial point to the final point. For example, this diagram is not like this. I don't have a single dashed line that goes from one end to the other because I have a crossing. But if you don't have a crossing, whatever line starts here will be the last one that ends there. And this means that my self-energy has this overarching dashed line, and everything inside which is covered by this line is the whole series for the same average green function. So it's just instead of G0, it's now this thick line, it's the full green function now. So self-consistent Born approximation means two things. Sigma equals, this is the equation for sigma, 1 over 2 pi nu tau integral over d dp by 2 pi power d of the green function of p. And the green function of p equals epsilon minus psi of p minus sigma inverse. These are two equations for two unknowns. G is one unknown, sigma is the other one. Two equations for two unknowns can be solved, and we can find the whole sigma, which includes all of that, and the whole green function that includes that sigma. And it's like the Born approximation. Sigma is exactly like in the Born approximation, just instead of G0, I put the full G here. That's why it's called self-consistent. It's like a Born, but it should be solved self-consistently for G and sigma. And once again, this includes all diagrams which do not have any crossing of the dashed lines, and we have shown more or less that these crossings give some small corrections, so neglecting them is a well-defined approximation. So let's do the calculation. So let's write out these equations, solve them, and find a more accurate green function, which includes some diagrams beyond Born approximation. Yep.
When actually enough to use only Born approximation?
This is a very good question. Let me solve this equation and then we can discuss it once again. You will see it right now. So this is a equation for sigma. I should take G and put here inside this integral. So I have 1 over 2 pi nu tau. Then, as usual, I replace this integral by the psi integral, nu integral over psi. And then here inside I have 1 divided by epsilon minus psi of p, sorry, minus psi without p, minus sigma. So this is an equation for sigma. Sigma equals this integral that contains sigma inside. This is the self-consistency equation. And actually, it's exactly the same integral as we had before. We had I0 here, now we have sigma instead. So it's just the same integral with a different object staying, with a different number staying in the denominator, but Otherwise, it's computed exactly the same way. And guess what? This integral has a real part which is not well defined, which will give me the real part of sigma, which I don't need because I can again include it in the renormalization of chemical potential. And then this integral has an imaginary part, which will give me an imaginary part of sigma according to this equation. So imaginary part of sigma equals, and then I should take some imaginary number here, which is either in the upper or lower half plane, and the value of this integral does not depend on how far I shift my pole, because the residue is still the same. So actually it's minus I over 2 tau, depending on whether it's retarded or advanced object. Sorry, imaginary part is minus or plus. Probably I should not put I here because I already took imaginary part. Yeah. Or I can write it, sorry, let me write it differently. It will be, the meaning will be the same, but I will just write it in the form similar to what we have. Sigma equals a number, which is real, a real number, minus or plus I over 2 tau. It does satisfy this equation.
On the diagram, just shift the real part of sigma, right?
Yeah, the imaginary part didn't change. So now this is the answer to your question. You are free to use Born approximation because it's already almost exact. Inclusion of all these other diagrams does not really change the imaginary part of self-energy, only the real part.
So why don't we use answer for imaginary part? Can you briefly explain that?
Okay, this integral here, just imagine, I compute an integral over d psi divided by psi minus I, say a, some number, a, from minus to plus infinity. And I would like to take the imaginary part of this integral. So, well, I will not literally take imaginary part. I will just subtract from here a conjugated integral such that the real part cancels. So it's minus d psi, psi plus IA. Yeah, this is the conjugated one. Then, if I combine the two integrals, plus I have 2IA d psi divided by psi squared plus a squared. Then you take your table of integrals or whatever you do this. This is the arctangents. This is 2I arctangents of psi divided by a, which should be taken between minus infinity and plus infinity. And at plus infinity, it's pi over 2. At minus infinity, it's minus pi over 2. In total, this is 2 pi I, and it does not depend on A. That's the trick. It does not depend on A. So no matter what number you put here, to the calculation is to say that sigma is that number. It does not depend on what was inserted here. Was it I0 or I over 2 tau or I times something else? The left-hand side does not depend on it and is the same for all numbers. For the imaginary part, yes.
But it works, and here the sigma is independent on momentum, right?
Sorry.
Until it does not include diagrams which depends on momentum.
Which is by
sigma,
definition Born approximation, and this upgraded Born approximation, they do not include such diagrams because they always are covered by a dashed line, which is momentum independent.
In principle, there are multiple possible real solutions to this self-energy?
No, actually, to find this real part, if you really need it, you should do something better than this psi integration. You should take the real spectrum, and then you can do it, and you will have some meaningful result. But
That doesn't affect
It-
the stability.
at least for usual metal with a big Fermi surface with a large Fermi energy, it's just some small shift of this Fermi level.
It will tell you how much the energy is.
Yeah. But in some other cases, when it's not such a good metal, or when the Fermi surface is very complicated and any shift can change the topology, it might be relevant. Okay, what time are we supposed to finish?
6.
At 6.
But we started at 4:15, so.
It's, yeah, I can stop more or less at any point. I'm just wondering, maybe everybody gets too tired already, maybe not. So, I so far explained how how disorder is treated on the level of the green functions, and how we compute the average green function, and actually it's quite simple. I mean, it's quite simple. And now we will discuss, for example, how the diffusion equation can be understood from this quantum mechanical perspective. Diffusion equation, or better to say the diffusion propagator, diffuson, was a classical propagator of a classical diffusion equation, and actually it can be, this is diffuson, it can be calculated quantum mechanically as well, because there is the following simple formula. D equals 1 over 2 pi nu. Two green functions, 1, 2. One of them retarded, the other one advanced. Average over disorder. I will not tell you where I took this equation from. It's called Kubo formula. It's some part of quantum mechanics, how to derive it. But you can believe me that it's correct. I mean, and there are many textbooks on quantum mechanics that discuss what the Kubo formula is. So, once again, the propagator of diffusion equation is related to the average product of two green functions. If you take retarded green function for the electron, it's the amplitude to go from one point to another point. If you take the advanced function going backwards, it's the same amplitude complex conjugated. If you multiply them, it's the amplitude absolute value squared, which is the probability. So actually this thing is the probability to go from this point to that point, averaged. This is exactly what a diffusion propagator tells us. What is the probability for a particle which starts here to diffuse and be found in some other point at some later time. Yeah.
Lost the picture of what's going on, because it's related to my question about what do you mean by averaging. And I thought that we have like periodic lattice, 3-dimensional, for example, and we put just one extra like stable particle, not electron, which is like impurity. And
Sorry, we put one impurity, you say?
yeah,
No,
so
we have
then
many.
We say we put here or there, and that's realization, and then the average.
No, sorry. Sorry, we have many impurities which have some density. We have 10 to power 20 impurities. Each impurity produces some potential. If you add up all these potentials together in a single function, this is what we call V. Our perturbation includes all impurities at once. But then we average over positions of these impurities or things like that.
So what do we need to average if
This is correct. But actually, it turns out that in many cases, you can compute not just an average quantity, like the average green function, you can also compute the mean, whatever, I forgot the name again, dispersion, the deviation from this average, so like average square. And for all these quantities that we discussed, this was also done, and it was shown that these deviations are very small. So actually, each quantity has a distribution which is very narrow peak around the average. So if you compute the average, it's more or less the same as you compute it in any given realization, with the probability of deviation being extremely small. This notion is called self-averaging. Quantities self-averaging means that in every realization, it is almost the same as the average. It's not true for every quantity, but in good metals, for these things, it works.
I understand it better. And that formula which you just wrote, so I thought Green's function is a propagator.
Yes, that's true.
And here we have diffusion is also propagator. It's a Kubo formula. So what is the propagator exactly? And what is the meaning of this D function if it's not a propagator?
No, it is a propagator. But it's a propagator of the classical particle.
It's a propagator for density.
It's a propagator of density, or in other ways, it's a propagator of the
Like where
School.
to write sidebar side.
cyber cell. Yeah. So it's like a 2-electron propagator, but taken 1 electron and 1 hole, if you like, one
Propagator for a different
Because
for a different operator. Yeah.
you start from classically, I imagine the same as quantum mechanics that we have electron, there are, as I say, a lot of impurities and it propagates, so we have Green's function.
Yeah, but the electron is a quantum object, and the green function, the propagator, is the propagator of the Schrödinger equation. And Schrödinger equation gives you the wave function, which has a phase. And to find the probability, you should take your wave function and square it, and this will give you the classical probability. So it's like a square of the propagator of the Schrödinger equation. Absolute value squared. I mean, retarded ones, it's perfectly fit for that.
Is that 2 pi mu?
Oh, 2 pi nu is, I just put it for proper normalization. Actually, you can remove it. It doesn't matter. I put it there such that the answer looks exactly like we had it from classical mechanics. But
Sometimes you write it
yeah, okay. So let's compute this thing. We have to average the product of 2 green functions. One is retarded green function, this upper one, and it should be a function of energy plus omega and momentum plus q. The other one is the advanced function just of energy and momentum. We average their product, and we integrate over all values of p, but not epsilon. And what we get should be the diffusion of omega and q. So how do we so far we found the average green function. Now we need the average product of green functions. How to do this? Well, the simplest thing to do is say, I don't care, let's average each function separately. I don't know how to average the product, I know how to average one of them. So I will replace the average product by the product of average, and this object I will call not D, I will call it B. B is a different letter which has no meaning. B is the same integral over all momenta. I will now write it immediately nu dxi of the product of 2 average green functions. And the product of 2 average green functions, I will also write it like this, epsilon minus xi. This is for the retarded functions. So I add plus omega, or let me put it this way, xi of p plus q plus omega plus I over 2 tau. This is the retarded function. And the advanced function is epsilon minus xi of p minus I over 2 tau. And xi of p is just xi, is my integration variable.
This is the ring with the 2 thick lines, right?
Sorry?
This is the ring with the 2 thick lines.
Yes. two thick lines. And this psi of p plus q, I should expand in q. Just let me finish this sentence. So this psi of p plus q is actually psi of p plus some small correction proportional to q, and the small correction is the Fermi velocity times q, is the scalar product. And psi of p is just the same psi, I mean the same variable that I'm integrating. Yeah, what's your question?
I just wanted to ask that in principle we can construct crosses from R and P.
Yes, we can.
And we do not call them here.
They are not included in B.
Yes.
Yes.
So this is just part.
Yes, that's why it's B and not D.
Okay. Yeah. Thank you. Got it. Sorry.
Minus 5p plus q, right?
Why this? Why I have Q here or what? Here?
Yeah.
Well, because it was the green function and the momentum was P plus Q.
Why minus? Or
Sorry. I mean, this psi is psi plus V of Q, and then minus will apply to both of them.
what do you have in brackets?
Psi of P plus Q equals
Yeah.
psi plus V Fermi Q. Approximately. So I will not do this in real time, but it's a very simple integral because, as usual, we take it by taking residues of the poles. We have one pole in psi in the upper half plane, the other one in the lower half plane. You can complete the contour in any direction you like. The answer does not depend on this. And actually, it looks like that. It's 2 pi nu tau divided by 1 plus I tau V Fermi Q minus I tau omega. It's just the difference of these two things. If you subtract this from that, you have I over tau plus V Fermi Q plus omega. I over tau goes to the numerator, and then this is what you have in the denominator. And for this object, we will assume that this tau V Fermi Q and tau omega, we will assume they are both much smaller than 1. We consider this at some low frequency and low momentum, and this will be approximately equal to 2 pi nu tau. I can expand in series. 1 plus I tau omega, I expand in this object, minus I tau V Fermi Q. And then the square of this will be plus tau squared V Fermi Q squared. This is a scalar product of two vectors, V Fermi times Q. I just expanded. And I still have to do, I already erased this, averaging over directions on the Fermi surface. Remember, there was this equation. So averaging over directions of Fermi velocity will actually kill this linear term. And the average of that one will be tau squared, V Fermi squared, Q squared, divided by D dimension. Just average over the sphere. Yeah? That's
The average comes from, where does the D come from?
D is the dimension of your space, 1, 2, 3.
Oh, so you have to average the vector squared, okay.
Yeah, it's cosine squared averaged. So scalar product has a cosine inside, it's squared. After averaging, gives you 1 over D. So this thing, once again, is 2 pi nu tau 1 plus or minus tau dq squared plus I tau omega. This is the diffusion constant, tau v Fermi squared over d. Okay, so this object is not like a diffusion propagator still, but already contains diffusion constant inside.
You know, it's right. You can see that what the diffusion constant is from it.
Yeah.
Because the pole is located.
Yeah, yeah. Well, it doesn't have a pole yet, but it will have in a second. So what is missing? Actually, what is missing is exactly what was asked previously, that we average the two green functions separately, but we have to include some correlations between them. Actually, what we do when we average, we take two green functions, we put impurities inside these crosses, right? And then we average, we connect crosses with the dashed lines. And we can connect two crosses like this, and this will be the part of the self-energy for this green function. We can connect crosses like this, or we can connect them between the green functions. And this possibility was not taken into account. We take just two green functions which include all possible self-energies, but we never included the lines that connect the two of them. And actually, we still have this notion that crossing of dashed lines is unfavorable, the same as we had for self-consistent bonds. So what we have to do, we have to connect the two lines, the upper one and the lower one, with the dashed lines, but such that they do not cross. So the only way to do this is called a ladder. We should add this series. So let's do it, and this will be the last thing for today. I restore 1 over 2 pi nu, and I write 1 over 2 pi nu. There is first term when I have 0 vertical lines, and this is called B, right? Then there is a second term when I have only 1 vertical line, and it's called B squared divided by 2 pi nu tau, because this vertical line is 1 over 2 pi nu tau. And I have 2 such bubbles. Then I have next term, which is B cube divided by 2 pi nu tau squared, and so on.
You mean that this is the sum of such a graph,
Yeah.
not the one?
Well, of course, I draw 4 lines here. I mean the sum from 0 to infinity. This is the usual thing to do it. Okay, so what do we have? This is a simple geometric series. We should start with the first term, b over 2 pi nu. This is b. Over 2 pi nu is just tau. Tau. Divided by 1 minus b over 2 pi nu tau, right? Looks correct to me. Equals tau divided by 1 minus b divided by 2 pi nu tau is just all I have here in the brackets.
Probably to multiply it by b, because if b is 0, the sum is 0, but the result is
B is this, and these two things are small corrections to unity. I just neglected them. B in the numerator, this one, the first one, is just 2 pi nu tau. And in the denominator, I will retain the small corrections because it just so happened that the unity cancels out. Yeah? 1 minus tau dq squared plus I tau omega. Just so happened that 1 cancelled out. That's why I need these small corrections. And they also contain tau, which also cancels. And I get exactly what I expected, namely the classical diffusion propagator. Here or here? Because I'm too lazy to draw 0, 1, 2, 3, and up to infinity, I just show a representative of this series. With many lines enough to understand that I have to sum all of them.
So if we consider the second term, b squared divided by
This one.
I, yes, this one, how would the diagram
This term is with 2 lines, and this term is with 0 lines, and they're all summed. This is this is 1b, these 2 green functions. This is the second b, and the vertical line is this denominator. Actually, this thing is a delta function, so it's a single point in real space. I can as well draw it like this. This will be a single point. Then it looks more like b taken twice. Yeah.
When we do the Taylor series on the calculated p,
This one.
also, yes, then also we would have like a d square term from omega, right?
Which term?
D square omega term, or d square omega.
The square of this one. Yes, we will.
Yes. And why we omit it?
Because it's small. I mean, omega tau is small. So I took first one, but the next one is much smaller than this one. And this one I take only because
Of the same order
no.
who is the, no, I mean like why this one is of the same order as d squared?
Because I didn't tell you how small is omega and how small is q. They are small in such a way that these 2 are of the same order. Look, this is a very good question, and I will give you some more explanations about this. So, if I remember what I wanted to say, actually. So this diffusion propagator, wait. Yeah. I started from saying that omega tau is small, and this V Fermi tau, V Fermi q is also small. Omega tau is small. L, mean free path, times q is also small. These are the assumptions that we used to derive this, to do this expansion here. Why do we need these assumptions? Because the diffusion equation that describes classical diffusion actually is an approximate equation. It's not the exact one. It's an approximate equation. And these green functions, they know much more than this classical approximation. They know about electrons, their phases, their interference, scattering on individual impurities. Diffusion, to really establish diffusion, you need to do many scatterings. When your electron scatters 10 times, then you can say it already forgot about its original momentum, it's already diffusing. But on the scale of mean free path, there is no diffusion, there is a ballistic motion. And on the time scale of tau, on times shorter than tau, there is no diffusion, there is just ballistic motion. That's why diffusion equation applies only when omega and q are small enough such that within one period of omega you have many scatterings, and within the wavelength of q you have many scatterings. That's why this should be small, and we can do this expansion, and only in that limit we recover the classical diffusion equation. And to your question, dq squared is of the same order as omega. They are both small, they are of the same order, exactly because in the diffusion equation, in the diffusion pole, we have the difference of them.
So like on
Yeah, it's not a real shell, it's not a Fermi surface, but yeah,
Sort of imaginary shell.
imaginary shell, yeah, if you like.
So if you take opposite limit, we will get ballistic transfer.
Yes, and green functions are still good, but diffusion equation is not, and you will not derive it
But
this way.
ballistic, I thought like impurity are not affected somehow. Or they're
Well,
affected.
if you have no impurities at all, completely clean, yes, you will have purely ballistic transport. The electron conserves its momentum and flies in the same direction indefinitely long. But I don't think you will need such a propagator then. It will be not interesting. I mean, you can.
This will be like 0, right, in the opposite limit.
Well, it would be like then you can just, then it's just a free theory. So then you can just,
Yeah, that's the question.
You can solve anything directly from the Schrödinger equation. You don't even need green functions in this case. You don't need any perturbation theory, any complicated summations. It's just very basic.
Last question. And why is this method is justified that we average separately Green's functions and then add this other?
No. Actually, I averaged them fully. I mean, I just show you some representative diagram when I have crosses, and I average the product of two functions. But the only thing I did, I took only the diagrams without crossings.
You said a V is when you average first Green's function, second Green's function, then you calculate.
B is the integral of the product of two averaged green functions. It's my definition. B is the quantity that I defined. I defined this integral, not defined. I wrote this integral and I say, let's call it this B. This is my definition of B.
Yes,
That's it.
Then you say like to get D, we need to also
We need-
average.
Yeah, because we have to include diagrams with 0 vertical lines, 1 vertical line, 2 vertical lines, and each diagram, for the diagram with 0 vertical lines is exactly B, how I defined it. And this one is exactly B squared over 2 pi nu tau, how I defined it. And if you sum them all, it means you included all diagrams which have all possible self-energies and all possible vertical lines, given that they do not intersect.
potential has no momentum.
So that's the definition of averaging.
Sorry?
That's the definition of averaging.
Definition of averaging means connect crosses with dashed lines. You have a diagram with crosses, it's not averaged. It's just V, 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 V. And then when you average, you connect crosses with dashed lines in all possible ways.
The definition of averaging here would be like pick a potential function, pick a function.
A functional integral of a potential with a Gaussian weight. Yes, you can do it this way. Okay. This is all for today. If we have no more questions, everybody is happy to leave.
So this 2 pi nu here is just for normalization.
Yeah, if I don't include it here, it will appear in the numerator. It does not.
What you're interested in is the pole, right?
Yeah, so the pole is the same as